Welcome back to the deep dive. This time, we're tackling something pretty abstract. Algebraic topology.
Yeah.
You've sent in a textbook chapter, some recent papers, even a few YouTube lectures. Ambitious.
Ambitious is right.
But that's what we're here for. We'll distill it all down to what you need to know.
Think of us as your translators. Algebraic topology can feel like a whole different language.
Oh, for sure.
But we'll make sure you grasp not just the vocabulary,
Yeah.
but how to actually use it.
All right, so level with me. I know topology is about the shape of things, but we're not talking lengths and angles like in geometry class.
It's deeper than that. Imagine you're looking at a protein molecule.
Okay.
Its precise shape is crucial, but so is how it folds.
Right.
That determines its function.
Okay.
Algebraic topology helps us analyze that kind of connectivity that goes beyond rigid measurements.
Okay, I'm intrigued.
Yeah.
The textbook starts with this classic problem.
Okay.
The Königsberg Bridge problem.
Yep.
It's about walking across all 7 bridges in a city without repeating any, and it turns out you can't.
You can't know. What's fascinating is how Euler solved this.
Okay.
He realized it wasn't about the bridge's lengths, but how they connected the land masses.
Interesting.
He boiled it down to a network of points and lines, essentially inventing graph theory in the process.
Wow.
And that's a core idea in algebraic topology,
Okay.
reducing complexity to its essential connections.
So it's like he zoomed out and saw the bigger picture, ignoring the irrelevant details?
Precisely. And this leads to powerful concepts like the Euler characteristic.
Okay.
It's a number that stays the same even if you stretch or bend a shape, kind of like a topological fingerprint. For simple shapes, like a cube, it's always 2.
Wait, so if I crumple up a piece of paper, its Euler characteristic is the same as a flat sheet?
Exactly. It's about deeper properties than just how something looks.
Okay.
And this goes way beyond just polyhedra.
Right.
The Euler characteristic helps us classify surfaces like distinguishing a sphere from a donut, based on the number of holes.
Okay, that's starting to feel more powerful than just counting edges and faces. Now, another term that keeps popping up is homotopy equivalence.
Yeah.
The textbook defines it, but I'm still a bit fuzzy on why it matters.
It's about recognizing when 2 spaces are essentially the same,
Okay.
even if their appearances differ.
Yeah.
Imagine deforming a coffee cup into a donut. You can do it without tearing or gluing. Right.
Right, yeah.
That's a homotopy. Showing those shapes are homotopy equivalent.
Well, would that oversimplify things?
That's a great question.
Don't we lose important geometric information by just focusing on whether we can deform one shape into another?
That's a great question. And it highlights the trade-off in algebraic topology.
Okay.
We gain powerful insights by focusing on essential properties, but we might lose some finer details.
Yeah.
The key is to choose the right lens for the problem at hand.
So back to those protein molecules. Maybe their exact shape does matter for some things, but for understanding how they fold and interact, homotopy equivalence could be enough.
Exactly. And that's where algebraic topology shines.
Okay.
It lets us pick the right level of detail.
Okay.
It's like having a toolbox with different magnifying glasses,
Yeah.
each revealing a different aspect of the structure.
Okay, I'm starting to see the appeal, but the YouTube lectures throw in even more terms. Homology groups, degrees of maps, fundamental groups. It's a lot to unpack.
Don't worry, we'll break it down.
Okay.
Think of these as increasingly sophisticated tools for analyzing topological spaces.
Yeah.
Homology groups, for instance, provide a more nuanced way to describe those holes
Right.
we were talking about earlier.
So not just whether 2 things have the same number of holes, but like the types of holes.
You got it.
Because a donut hole feels fundamentally different from, say, the hole formed by a loop of string.
You're exactly right.
Yeah.
A donut's hole is trapped inside.
Right.
Well, you can slip the string off. Homology groups capture that kind of distinction.
Okay.
And the degree of a map helps us measure how many times one space wraps around another.
Okay, my brain is doing loop-de-loops now. It's mind-boggling to imagine how this abstract math applies to real-world problems.
Oh, the applications are exploding.
Oh, wow.
Data analysis, robotics, even understanding the structure of the brain.
Wow, okay.
We'll get to those, but first, let's solidify a few more key concepts.
Okay.
One concept that seems to bridge geometry and algebra is the tangent bundle.
Yeah, that one's still a bit hazy for me.
Okay.
The textbook mentions it in passing,
Right.
but I'm not sure I grasp the significance.
Imagine an ant crawling on a smooth surface, like a sphere.
Okay.
At each point, the ant can move in certain directions.
Uh-huh.
Those directions form a tangent plane set.
Right.
The tangent bundle is like collecting all those planes together.
Okay.
giving a global picture of how movement is possible on the surface.
So it's not just about where the ant is, but what directions it can go from that point?
Exactly. And this bundle turns out to have a natural structure of a vector space at each point,
Okay.
making it a vector bundle.
Okay.
This lets us apply linear algebra to understand the geometry of the surface.
Okay, I see how that links different mathematical ideas together.
Right.
The sources also mentioned something called the cotangent bundle.
Yeah,
Is that related?
it is. Think of the tangent bundle as describing motion.
Okay.
The cotangent bundle is its dual.
Okay.
It's about measuring things on the surface.
Okay.
Like instead of the ant's velocity, we might consider the gradient of a temperature field. That's a cotangent vector.
Interesting. So one's about movement, the other about measuring changes?
Precisely. And this leads to differential forms.
Oh.
Those things you mentioned for calculus.
Right.
They live on the cotangent bundle and are crucial for things like integration, curvature,
Okay.
and even electromagnetism.
Okay, now that's linking back to things I'm more familiar with.
Right.
But the papers jump into some pretty heavy-duty stuff. Diram cohomology. Does that build on these ideas?
It does. Diram cohomology uses differential forms to study the topology of smooth manifolds.
Okay.
It's like a sophisticated upgrade to homology groups.
Right.
Instead of chains of simplices, we're using these differential forms to detect holes and other features.
So it's like we've gone from counting bridges to studying the flow of air over a wing using calculus.
You're getting the gist. And what's amazing is Diram's theorem.
Okay.
It says this fancy calculus approach gives the same answers as the more combinatorial homology groups.
Huh.
It's a bridge between different areas of math.
All right, that's pretty profound.
Yeah.
Now, you mentioned applications earlier.
Right.
The sources hint at algebraic topology being used in data analysis.
Yeah.
I'm struggling to imagine how that works.
One technique is persistent homology.
Okay.
Imagine a cloud of data points.
Okay.
It might have clusters, gaps, even holes in higher dimensions that we can't visualize directly.
Yeah. Okay.
Persistent homology tracks these features as we zoom in and out, revealing the data's shape at different scales.
So it's like finding the topological fingerprint of a data set, revealing underlying structure that basic statistics might miss.
Exactly. This is used in everything from analyzing protein structures to understanding social networks.
Wow.
And another tool is Mapper.
Okay.
It creates a simplified map of a complex data set, highlighting important features and clusters.
Okay. That's starting to feel more concrete.
Yeah.
What about robotics? The sources mention motion planning.
Think of a robot arm moving in a factory.
Okay.
Has lots of joints, so its configuration space, the set of all possible positions,
Right.
is high dimensional.
Okay.
Algebraic topology helps us understand the shape of this space so we can plan paths for the robot that avoid obstacles and are efficient.
So it's like finding a route through a complicated maze. But the maze is made of all the robot's possible movements.
Precisely. And this applies to self-driving cars, too.
Oh.
Understanding the topology of the environment and the car's possible motions is crucial for safe navigation.
Okay, those are some seriously cool applications.
Yeah.
But the sources also dip into knot theory, which feels like a whole other topic.
It is its own field,
Yeah.
but deeply intertwined with algebraic topology.
Okay.
A knot is just a closed loop in 3D space,
Right.
but classifying them is surprisingly difficult.
Okay.
We use things like knot groups,
Yeah.
which are algebraic objects,
Right.
to distinguish different knots that can't be formed into each other.
So like a simple overhand knot versus a figure 8 knot would have different knot groups.
Exactly. And they're even more powerful invariants, like the Jones polynomial,
Okay.
which also arise from algebraic topology,
Right.
allowing us to distinguish even more subtly different knots.
It's incredible how these seemingly disparate areas keep linking back together.
It is.
Now, the YouTube lectures get into some pretty mind-bending stuff. Homotopy groups of spheres.
Yeah.
Is that as abstract as it sounds?
It's abstract,
Yeah.
but fundamentally important.
Okay.
Think of all the ways you can wrap a rubber band around a ball without tearing it.
Yeah.
Each is a representative of an element in a homotopy group.
Okay.
These groups tell us about the essential ways to map one sphere into another.
But why focus on spheres? They seem so simple.
They're the building blocks.
Okay.
Understanding their homotopic groups gives us insight into more complex spaces,
Right.
and it's surprisingly difficult.
Oh, really?
We still don't know all the homotopic groups of spheres,
Wow.
even after decades of research.
That's a bit humbling, honestly.
It is.
And then there's stable homotopy theory.
That's where things get really deep.
Okay.
It's like zooming out to the big picture of homotopy theory.
Okay.
We focus on properties that remain stable as we increase the dimension of the spheres.
Okay, I'm getting a sense that stable homotopy theory is like the ultimate form of homotopy, where we're looking for the most fundamental and unchanging properties.
Precisely. And it turns out this seemingly abstract theory has connections to profound questions in mathematics and physics.
Wow.
It's a testament to the power of abstraction to reveal hidden connections.
Well, my head is definitely full of new connections after all that. We've covered so much ground.
We have.
But I'm curious, what are you most excited about in algebraic topology right now? What are the frontiers?
One area that's exploding is the application to materials science.
Oh, wow.
Topological materials, like topological insulators, have properties determined by their shape in a very deep way, leading to potential breakthroughs in electronics and beyond.
So the math we've been discussing is being used to design real-world materials with bizarre and useful properties.
Exactly. And another incredibly exciting area is the connection to string theory.
Oh, okay.
The extra dimensions that string theory predicts are topological objects.
Right.
And algebraic topology is the perfect language to describe and study them.
Wow. So this math is literally being used to explore the fundamental nature of the universe.
It is. And it highlights how algebraic topology is not just about abstract shapes,
Right.
but about understanding structure and patterns at the deepest levels.
Before we get too lost in the cosmos, the sources also mention some surprising applications closer to home.
Yeah.
One thing that caught my eye was the mention of algebraic topology being used in neuroscience.
Yeah.
Is that really a thing?
It is, yeah.
How can you apply these abstract ideas to something as complex as the brain?
It's becoming a major area of research.
Really?
Think about the connectome,
Okay.
the map of all the connections between neurons in the brain.
Okay.
It's a massively complex network,
Right.
and understanding its structure is crucial for understanding how the brain works.
So we're not talking about the physical shape of the brain itself,
Right.
but the network of connections within it.
Exactly. And it turns out the tools we've been discussing, like homology and persistent homology,
Yeah.
are perfect for analyzing these networks.
Right.
They can reveal clusters of neurons that function together, identify critical pathways,
Right.
even detect changes in connectivity due to learning or disease.
Oh, okay. That's blowing my mind a bit.
Yeah.
So we can use topology to see patterns in how our brains are wired.
It's still early days.
Yeah.
But the potential is huge.
Wow.
And it's not just the brain.
Oh.
Algebraic topology is being applied to all sorts of biological networks,
Okay.
like gene regulatory networks
Right.
and protein interaction networks.
It's amazing to think that math developed for studying abstract shapes
I know, right?
could be so powerful for understanding the complexity of life itself.
It really is.
And it doesn't stop there.
No, it doesn't.
Another surprising application is in the field of fluid dynamics.
Okay.
Think about the swirling patterns of turbulent flow.
Yeah.
They seem incredibly chaotic.
They do seem chaotic, right?
Yeah, turbulence is kind of a nightmare scenario for a lot of engineering problems, isn't it?
It is, yeah.
Yeah.
And traditional methods often struggle to capture its complexity. But algebraic topology provides new tools for analyzing these flows,
Okay.
for identifying coherent structures,
Right.
tracking their evolution, and maybe even developing better predictive models.
So instead of just seeing chaos, we can use topology to find hidden order within the turbulence.
Exactly. It's like finding the signal within the noise.
Wow.
And this has implications for everything from weather forecasting to designing more efficient aircraft.
Okay, color me impressed. But I have to admit, some of these applications still feel a bit out there.
Yeah.
Like the sources mention algebraic topology and computer graphics.
Right.
How does that work?
It's more intuitive than you might think.
Okay.
Imagine you have a complex 3D model with millions of polygons.
Okay.
For video games or animation, that's a lot to process.
Yeah.
Mesh simplification uses algebraic topology to identify areas that can be simplified
Okay.
without losing the overall shape.
So it's like compressing the 3D model without sacrificing too much detail.
Exactly. And it's based on the idea that certain parts of the model are topologically uninteresting. They don't contribute significantly to the overall shape.
That's clever.
Yeah.
It seems like you're always looking for the essential features.
Right.
The parts that really matter.
That's the essence of algebraic topology.
Mm.
And this way of thinking is proving useful in more and more areas of computer science,
Oh, wow.
like image analysis, machine learning, and even cybersecurity.
Speaking of mind-blowing applications, The sources mention something called topological quantum computing.
Ah, yeah.
That sounds straight out of science fiction.
It's cutting-edge stuff.
Okay.
But the basic idea is this.
Yeah.
Traditional quantum computers are very fragile.
Right.
Any disturbance can cause errors.
Yeah.
Topological quantum computers aim to use the properties of certain materials
Okay.
to create quantum bits that are inherently protected from noise.
So it's like the information is encoded in the very fabric of the material, rather than in delicate quantum states that can easily be disrupted.
Exactly. And algebraic topology provides the tools to understand and classify the topological properties of these materials,
Okay.
guiding the search for suitable candidates.
Wow, so this math could literally be the key to building the next generation of quantum computers.
It's a possibility,
Yeah.
and a very exciting one.
Yeah.
It shows how this seemingly abstract field is connected to some of the most revolutionary technologies on the horizon.
Honestly, this whole deep dive has been a revelation.
I'm glad to hear that.
I started out thinking algebraic topology was just about shapes and holes,
Right.
but it's clearly so much more than that.
It is, yeah.
It's a powerful way of thinking,
Mm.
a language for describing structure and patterns that permeates so many areas of science and technology.
Yeah.
And it sounds like we're just at the beginning of understanding its full potential.
Absolutely. New applications are being discovered all the time.
Yeah.
Who knows what the future holds for this amazing field?
Well, you've certainly given me a lot to think about.
It's been my pleasure.
And a whole new appreciation for the power of algebraic topology. Thanks for guiding me through this incredible landscape of ideas.
You're very welcome.
To our listeners, we hope you've enjoyed this deep dive into algebraic topology. We've only scratched the surface, but hopefully we've sparked your curiosity to explore further.
And until next time, keep those brains stretching.